Thing is, let me remind you that Monday is Labor Day, so there'll be no class on Monday. So we meet again a week from today. Second, are there any questions from last time? So that means everything last time was clear? Okay, so let me review where we were last time and then continue. So what we were doing was we were looking at the method of rate up equals rate down. And this was an intuitive method by which we could derive the state probabilities for a queuing system. And the particular system we were looking at was one where we had a group of servers and customers arriving at random. And if the customers are blocked, that is, if they find all the servers busy, then they overflow. And we wrote equations which, for each state, related the rate up from that state to the rate down from the state above it. So in general, it looked like this. Lambda pj, that would be the fraction of time or probability I'm in state j, times the arrival rate, which would give me the rate at which arrivals occur, find the system in state j, and make the system move to state j plus 1. So this is the rate up from state j. And that was equal to the rate down from state j plus 1. So pj plus 1 is the probability that you're in state j plus 1. And then if you are, the aggregate service completion rate is equal to 1 over tau, where tau is the average service time, per customer in service. And since there are j plus 1 customers in service, then there would be j plus 1 over tau. That would be the service completion rate. So last time we wrote these equations, except we didn't write them in general. We wrote lambda p0 is equal to 1 over tau p1. Then lambda p1 is equal to 2 over tau p2, and so forth. But these are the general equations for j equals 0, 1, 2, and so forth, up to s minus 1. S minus 1, that's the last equation. That's the rate up from state s minus 1 equals the rate down from state s. The assumption is that we have s servers here. And then we solved these equations. And the equations were, the solution is pj is equal to a to the j over j factorial p0, where a is equal to the product of the arrival rate and the average service time. So that's just the definition of a. And it turned out that way because when you solve these equations, the lambda and the tau always appear together as a constant. So you simply name that product a. Now, this gives you the probability for any state in terms of the probability for a single state, the 0 state. But in order to get numbers out, you have to have a numerical value for p0. And so that's determined by another equation called the normalization equation, which says simply that the sum of all of these probabilities must add up to 1. So if I substitute this into here and then solve for p0, I find that p0 is equal to 1 over the sum of terms of the form a to the k over k factorial as k runs from 0 to s. So now I know what all the state probabilities are. And in particular, I'm interested in the one, at least in this application that I mentioned, PS. This is the probability that I'm in state S, meaning that all servers are busy. And that's given the name. That's an important formula. So it's called B of SA. This is the famous Erlang B formula. And parameters are S, the number of servers, and A, this product, which is a so-called offered load. Obviously, it's a measure of demand. And then if you write this out, that means the probability we're looking at is given by a to the s over s factorial divided by the sum a to the k over k factorial as k runs from 0 to s. So this is the important Erlang B formula. Now, telecommunications engineers use this because this is a classic model for a telephone system in which the servers are trunks and the arrivals are calls. Lambda is the call arrival rate, the rate at which the calls come into the central office and request the use of a trunk, and tau is the average length of a phone call. And so the Erlang-B formula then gives the probability that all trunks are busy. And in fact, you can draw a graph of this and compute these things. Here's the A, which is the demand on the system. Here is the probability of blocking, the Erlang-B value. Since that's a probability, that means these numbers lie between 0 and 1. And then if you were to graph this function for each different value of S as a function of A, you get this family of curves. So there's S equals 1, S equals 2, S equals 3, and so forth. So the way the telephone engineer would use this is he'd say, well, I have a particular estimate of my offered load right there, and I have a criterion, like 1% probability of blocking right here. And so I want to find the curve that goes through that point. But in general, there's no curve that fits through any arbitrary point. But there will be the first curve below that point, and that's the one that you would take because that value of S then would produce for this offered load a value of the probability of blocking that's less than the criterion. And if you had one less trunk, then you would have the curve above that point, and that would not meet the criterion. It would give you a probability of blocking greater than the criterion. Okay, so we went through all of this. And then I said that now we get this answer, and we derived this by using the rate up equals rate down argument. And then I wanted to go back and compare that argument with what I said are the essential parts of the model in queuing theory. So there are three parts in the simple model. One is the input process. So that's the thing that describes the way in which the customers request service. And the second is the service mechanism. So the input process describes the arrivals. The service mechanism describes the service. And then the queue discipline describes what happens to the blocked calls or blocked customers. I go back and forth in language between calling them customers and servers and calling them calls and trunks, because the primary application for this stuff is in telecommunications. And in fact, when I learned this, I learned it in the telecommunications context. So we always talked about calls rather than customers. But in general queuing theory, the customers, of course, can be anything. They don't have to be telephone calls. Okay, so these are the three parts of the queuing model. And I wanted to see how those parts of the queuing model relate to that formula. So the first question was, what was the input process? And the argument went something like this. Well, the input process is supposed to describe the random process that represents the calls arriving. So he said, well, we could have an input process that looks like this. So what I'm trying to show here is some kind of random variability. But we could have an input process that looks like this. And suppose, for example, that I imagine that this is my unit of time and that these patterns are repeated as time goes on. Sort of repeated, not exactly, but basically. And what you see here is that both of these patterns have the same arrival rate because they both give you 6 arrivals per unit time, but here they're bunched together and here they tend to spread out. And in fact, you could look at an extreme case in which they are exactly evenly spaced, like that, say. Now it's clear, intuitively clear. This is part of the problem here because my argument is that, well, this is a very subtle subject, so you got to be careful. Now it's clear to me that even though each of these cases has the same lambda, that they're going to produce different probabilities of blocking. Because what causes blocking? What causes blocking is when the customers want to use the server simultaneously. So if everybody arrives at the same time, then you're going to get the most overflow, the most congestion. And it's intuitively obvious that the system will provide the best service when the customers arrive spread out as evenly as possible. So the equations do not apparently reflect these differences, because in the equations, the arrival rate, the input process, is expressed solely by lambda, which is just the arrival rate. It's an average, and it's the same in each one of these cases. So therefore, that raises some questions, because if you look at the answer says that the arrival process, the input process, does not affect the probability of blocking except through its average value. And since all kinds of processes can have the same average, the average doesn't uniquely define the process, that implies several possibilities. So we're still talking about last time's lecture. So if I continue this process, that means that I'm going to really have to talk fast by the middle of the course, because I have to repeat the whole course up until that time. So we're going to see the same thing getting faster and faster. Eventually it approaches infinity and so on. Okay, so what are the possibilities here for the fact that this input process is reflected in the answer only through its average value? So one possibility is that it's the wrong answer. That is, that this method is wrong because the method seems to say that the probability of blocking does not depend on the variability, the statistical variability of the arrival process, and intuitively, you know, they can't be right, so therefore the method must be wrong. The second possibility is that, in fact, it's right in that, contrary to your intuition, it just turns out to be true that no matter how variable the input process is, the variability does not affect the answer. And so this is what you might call an amazing theorem, because it would say that the probability depends only on an average of a distribution and not on the higher moments of the distribution. So I'll call that amazing theorem. In fact, if it were true, what this would be is something called insensitivity. In other words, the performance measure is insensitive to some underlying factor, some distribution, some variability that you would think ought to affect the answer but doesn't. So whenever this happens, if it does happen, then this is very important. It's important from a mathematical point of view, because how do you prove that some performance measure is insensitive to some underlying quantity that's in it that nevertheless doesn't seem to matter? So that's surprising when it happens, and so it's difficult to could be difficult to prove it, and it's of mathematical interest. It's also of practical interest, because what more could you tell an engineer than something that he thinks he has to worry about, he doesn't have to worry about, is irrelevant, so you can toss it away. So this is another possibility. And the third possibility is something else in between. Okay, so what's that? This says that it's wrong always. This says it's right always. So the only other possibility is that it's right sometimes. In other words, there's some cases for which this is correct. Okay, so then we took a vote, being democratically oriented group. We took a vote on which of these three things is correct. So of course nobody voted for wrong, because if it's wrong totally, then I wouldn't waste your time thinking about it. Okay, so it's not wrong. The question is, how many people think it's right, an amazing theorem? And I guess nobody voted for amazing theorem, so everybody thinks that it's right sometimes. So if it's right sometimes, then that raises other issues, because if it's right sometimes, well, what are those times? And I guess it raises three questions. One is, when is it right? Another is the time for which it's right important? Is that actually an important particular input process, or is it some special bizarre one? And the third thing is, if it's right for that process, then what about the other processes? Then you have to go through some other argument, and you have to understand why it's right for one process and not right for the others. So these are questions that remain to be answered. And the answer is, although we have to prove these things and understand them better, that's what the course is about, is that this is in fact right sometimes. And the sometimes is for what's called a Poisson process. And so we have to understand whether or not, in fact it is, a Poisson process is a good model of reality. It represents this middle case here. And we have to understand why the process, that is why rate up equals rate down, works for Poisson process but doesn't work for other processes. And also how sensitive it is to other processes. That is, suppose I had regular arrivals, how far wrong would my answer be? And how would I calculate the corresponding probability for input processes that are not Poisson? So all of those questions arise. Okay, so that's where we were last time. And now we're going to move to the second piece, which is the service mechanism. So we want to see where the service mechanism is embodied in these equations. So first of all, let's see, are the servers are all in parallel here, because, and we don't care, and the servers are all statistically identical. That's reflected by the fact that I represent things only by the total number of customers present and not which servers they're using. So the servers are in parallel because when I have two customers in service simultaneously, the aggregate service completion rate is twice as large as when I have one customer. So by making the service completion rate proportional to the number of servers, then I'm saying, well, I don't care which servers they are, and they all have the same effect, and they're all running in parallel with each other. So that part is simple. That's taken care of. But the interesting part is the part that's analogous to what we did with the input process. That is, what about the length of time that, that's required for the service of a customer? And the answer is, well, we specified that in the equations through tau, and tau by definition was the average service time. Now, I was a little bit flaky when I went through this, because remember, this is an intuitive argument. So intuitive arguments, you can present them nicely in speaking, because you don't have to be very precise. You just have to be convincing. Like a politician, you just have to have the right flow. Nobody actually examines what you really said. And so the same thing is true here. So I can argue intuitively, and things sort of make sense, but then when you ask yourself, well, exactly what was said, well, it's maybe not that clear. So I said that, well, let tau be the average service time, and then if tau is the average service time, then the service completion rate per customer should be 1 over tau. Everybody bought that, okay? But mathematically, I'm not sure what that's not much of an argument, that's just a statement. And I haven't even defined what I mean by average. But it is clear that in the equations I have only this single value to represent the service times, which means that I haven't represented the variability of the service times any more than I represented the variability of the arrival process. That is, if tau is the average service time, then I could have a tau, let's say, of 10 minutes by having every call last exactly 10 minutes, or I could have half the calls last 1 minute, half the calls last 19 minutes. I'd still have an average of 10 minutes. So again, we come up to exactly the same question, because what we have is equations in which the service times are characterized only through a single parameter, which is their average value. And so that means since there can be service times, well, what are the possibilities? Service times could be constant. That is, here the inter-arrival times are constant. Now I could say, well, the service times could be constant. Every service time is the same. Or, if you look at this, which is supposed to represent the Poisson input, Poisson process, it turns out that if I have a Poisson process, we'll study this in detail later, that means that the times between these arrivals are exponentially distributed. So, just as it turns out that this particular formula requires, is correct, if I have exponential inter-arrival times, I might also have exactly the same kind of variability for the service times. That is, the service times might be exponentially distributed. Or they might have some other distribution, which could be more variable or less variable. I mean, the service times could be uniform or normal or gamma or hyper-exponential or, I mean, anything. So the question is exactly the same questions we asked before. One possibility is that since the answer does not reflect the variability of the service times, clearly it's not right, so it's wrong. So how many people think that this formula that I got doesn't work for any service time distribution? There's no case for which this is correct. Okay, same answer as before. I wouldn't waste your time going through this if it's wrong. Next. Second possibility, just like before, is that it could be an amazing theorem. In other words, it could be that the answers are in fact insensitive to the service time distribution, meaning that it doesn't make any difference whether the service times have no variability, they're all exactly the same, or they have some kind of total random variability, like exponential service times, or they're highly variable with a lot of bunching and spacing. In other words, a lot of short service times and a lot of long service times with an average someplace in between. So how many people think that this is in fact an amazing theorem and that this answer works no matter what the distribution of service times is? We got one person voting for that. Okay. And so the other possibility is sometimes. Sometimes means that there is some particular distribution or family of distributions for which this works. And if so, then we have the same question. What is that family, or what is that distribution? Is it a realistic one for describing reality? Why does it work in that case and not the other cases? And what about the other cases? So how many people think it's sometimes? Okay, so that's everybody else. So I'll put the this set complement. And if it is the other thing, does anybody have any clue as to what it is? What distribution does this work for? Okay, what most people would say, especially if they have some prior knowledge, is that the requirement is that you have exponential service times. Just like in the arrival part, you must have exponential inter-arrival times. But it turns out that, in fact, you're right, this is an amazing theorem, and that although you would expect some kind of symmetry between the input process and the service times in terms of sensitivity, it's not true. This formula is correct if you have Poisson input, but the service time distribution can be anything. No matter what distribution I had for the service times, if I were to actually derive this formula from first principles using a mathematical argument instead of this intuitive physical argument, then it would turn out that everything would cancel out except the average value of the service times. But the total distribution is irrelevant. So that is truly amazing, and it's very useful. In fact, this is like the ideal use of mathematics, because from a mathematician's point of view, the question of insensitivity is one that's the kind of thing mathematicians like to do. They don't like to calculate things or use things. They like to prove things, especially things that are surprising. And from the engineer's point of view, this is also very important, because what more could you ask for than someone to tell you that a formula that you have applies more broadly, more widely, is more robust than you might think. So that is one of the subtleties of the course now, or the subject, because at first glance it appears that the answer to this and this should be the same, but they're not. So we got to understand how you prove insensitivity, what it means, why it works, and when it works and when it doesn't. So you can see that the rate up equals rate down argument captures something, but it doesn't capture anything. There's a lot of stuff going on behind the scenes here that has to be investigated. And these are questions that wouldn't come to mind for an ordinary person. You have to already be thinking mathematically to be asking questions like this. But once you realize that the questions are there, then you see that they're really important questions. You can't apply these formulas in queuing theory with any confidence unless you know the answer to these questions, or at least are aware of the existence of these questions. Okay, any questions about that? Or this stuff is in chapter 1. So if you read that, it says that. So are the questions here clear? You're being convinced that there are subtleties in this course. Yes? You don't know why that's true. I didn't say why it's true because I can't at this level. What I'm doing now, the overview of this lecture is I'm giving you an intuitive method for solving what everybody agrees is a practical problem. See, this is intuitive because it's just high school algebra, and anybody who's smart can understand rate up equals rate down. There's no real mathematics in here, no derivatives or continuity or anything like that. So the subject lends itself to intuitive analysis, but the intuitive analysis completely overlooks these questions. So now that we realize that these questions are there, now this gives us focus to go back and now investigate this stuff in more detail and understand these questions. Now let me give another example of a subtlety. Okay? I said this is important, has its name, it's the Erlang-B formula. The reason it's important is because telephone traffic engineers use it to predict the fraction of calls that will be lost if in a real system. So the question is, how would I actually measure this? I mean, what do these probabilities represent? If I tell you that the Erlang-B formula is 0.1, 10%, what does that mean? Okay, that's one way of looking at it. One possibility is that this number represents the fraction of arrivals who, when they arrive, find all the trunks busy, and so they're lost. But when I talked about it, I didn't really say that. Actually, I said it. This is the tricky, intuitive politician's argument. There's really two different interpretations depending on whether I'm looking at this side of the equation or this side of the equation. I just said it in words. I didn't dwell on it. But here I said, okay, if this is the probability that I'm in state J, then what that means is that the rate at which the customers arrive, find the system in state J, and therefore make the system jump to J plus 1, is that probability multiplied by the arrival rate. So what that's really saying is that these customers arrive, and the probabilities represent what they see when they arrive. So if I were to calculate things that way, then the probabilities represent the fractions of arriving customers who find the system in each state. So that would mean that this is the fraction of arrivals who find the system in state S and therefore are cleared from the system. But on this side, I didn't call it the fraction of arrivals, I call it the fraction of time. Because here the argument is that if I'm in state J plus 1, if that's the fraction of time I'm in state J plus 1, whenever I'm in state J plus 1, that means that there are J plus 1 customers in service, and if each of them has service completion rate 1 over tau, then the aggregate service completion rate is 1 over tau multiplied by J plus 1. And so I took the aggregate service completion rate and multiplied that by the fraction of time that that aggregate completion rate applies, the fraction of time I'm actually in that state. So I interpreted this P as a fraction of time and this P as a fraction of customers. So I actually used a different argument on each side of the equation. So the question is, well, which one is it? In fact, I probably shouldn't have used P's here because from now on I'm going to represent these probabilities by two things. There's the PJs, which represent the fractions of time, and the PiJs, which represent the fractions of customers. So PiJ is the probability that the system is in state J when a customer arrives. So it's going to be the fraction of customers who find the system in state J. PJ represents the fraction of time the system is in state J. So it represents the viewpoint of the outside observer. Okay, so imagine somebody who is watching the system over all time or sampling at random and calculating the fraction of time I'm in each state. So in fact, if I drew a picture, okay, let's say that I start out in state 0. So the first customer arrives, he takes me to state 1. I stay there a while. Another customer arrives, takes me to state 2. I stay there a while. Then maybe somebody finishes his conversation. I drop down to state 1. I might stay there a while. I might have another arrival and go to state 2, another arrival, state 3, and so on like that. Okay, so every jump up is an arrival epoch. Now, from the outside observer's point of view, let's say that this is state S right here. And an arrival who occurs when the system is in state S, that's a lost call. So there's an example of what the system might look like. Okay, now, from the outside observer's point of view, the way he would calculate the probability of being in state S is you would take the total time that I'm in state S, divide by the total time of the observation. That would give you the fraction of time I'm in state S, and the same for each state. Also, you would expect that if the outside observer simply samples the system at random and observes, keeps a record of what he sees, then Pj would be the fraction of time that he would see state J. So if he samples at random, then the fraction of time he finds each state is the same as the fraction of time that the system is in each state. But that's from the viewpoint of the outside observer. Now, what about the arriving customer? The arriving customer is really what you're interested in here, because, or maybe what you're interested in, often what you're interested in, because you're trying to give service to the customer who arrives. And so what you care about is what the state of the system is when customers arrive and want to use the system, rather than what the state of the system is when at random points in time. So if I look at the system from the viewpoint of the arriving customer, I don't see it averaged over all time. I see it only at the points at which jumps up occur, because those are the arrival points. So the arriving customer's viewpoint is not necessarily related to the outside observer's viewpoint. I mean, if I calculate the fraction of customers who overflow, in this case it would be 2 divided by 2, 4, 7. So for this model, P sub S would be 2/7. Excuse me, pi sub S would be 2/7. What would P sub S be? Well, it would be the ratio of that divided by that. Is that 2/7? Well, maybe it is, maybe it isn't. But it's measured a different way. So in general, it would certainly be a different number. But whether it's the same number in distribution and only differs because of a finite measuring period, or whether it's theoretically different or theoretically the same, those are questions that haven't been answered. In fact, I can show you that the p's and the pi's don't necessarily have anything to do with each other, whatever. Let's take a simple computer science model where what you have is you've got a terminal and a CPU. Okay, so this is like the stupidest queuing model because there's only one terminal and there's one server. So when the terminal wants to use the CPU, that's a request for service, and he holds it for his service time, which in that case would be the job processing time. And then when he's finished, he goes back to his think state, so-called think state, and then he just sits there and he thinks, and then when he's ready to use the CPU again, he goes back and does it. Okay? He doesn't have to worry about any queuing here because there's no other terminal to interfere with him. So this is in a sense, this is like a boundary case. It's a queuing model which is so simple you don't really need any mathematics to do it. And of course, in these kind of problems, you often get a lot of insight by looking at the boundary cases, the extreme cases. So let me draw the diagram that corresponds to this. This is now the state of the system. This is just like a system where there's one subscriber, one telephone customer, and one trunk. As long as there's no other subscribers, then this guy is never going to be blocked when he wants to make a phone call. So now what does the system look like from his point of view? Well, let's say he's idle, and then he makes a request to use the CPU or make a phone call. And of course, the CPU is available, so he makes it busy. And then he hangs up, he finishes, and then it's idle. And then sometime later, he makes another request, and you get a diagram that looks like this. Okay, now, in this case, what's the pi? Call it pi 1. What's the fraction of arriving requests that finds the server busy, finds system in state 1? It's 0. Nobody's ever blocked in this case. What's pi 1? Pi 1 is the fraction of time that the system is busy from the viewpoint of the outside observer. If he sampled at random, it's the probability that if someone sampling at random finds the system busy. Well, I don't know what it is, but it can be any number between 0 and 1. So in this case, the p's and the pi's have no connection to each other whatever. And yet intuitively, it seems reasonable that they should somehow be related to each other. So then the question is, well, what we did here is we made an argument in which we have these, which I called p's, but actually I interpreted the right side as a p, but I interpreted the left side as a pi. I just sneaked it by you because you weren't being critical about the use of my language. So now the question is, well, which is it? Is it the p? Is it the pi? How do I interpret those things? Since I mixed them up in the argument, maybe it doesn't work at all. Okay, the answer is that if Poisson arrivals, or if Poisson input, then they're equal. That's a major theorem. The converse is not necessarily true. In other words, if they could be equal and not have Poisson input. But in general, if you don't have Poisson input, then they are not equal. But if you have Poisson input, then they are equal. Of course, that's very powerful. That shows that well, first of all, we needed the Poisson process in order for this formula to mean anything. And now what we conclude from this, although nothing's been proved, is that this formula will be valid if we have Poisson input and if the service times have any distribution whatever. And furthermore, whatever number this is has two interpretations, even though it will be measured differently under those two interpretations. Namely, if I measured the fraction of time that all servers are busy, or measured the fraction of arriving customers who find all servers busy, I'd get the same answer, even though they're totally different measurements. And third, I claim that the assumption of Poisson input, which is now, you can see, is critical, is also a good model of reality. I want to argue that unless there's evidence to the contrary, it's the best possible model of customers arriving at random. It's analogous to, say, in if you were describing a coin tossing experiment, you would say that heads and tails are equally likely unless you had some data that says they weren't. Or if you chose a card from a deck, you would assume that each card has probability 1 over 52, unless there was some reason to think that it didn't. So without with making the least restrictive assumptions you can make and going through a mathematical derivation, the Poisson process will be what will fall out. Okay, so that's where we stand at this moment. Any questions about this now? Okay, so now we got two branches we can take. One is to understand better what this means, and the other is to apply this to other cases. And so in the previous course, we spent a lot of time doing that, and I want to do that same thing, only a little bit faster. So the first thing I want to do is I want to describe what it means. And giving other examples of this, well, there's an exercise in the book. In fact, if you look at Chapter 1, in Chapter 1, the Erlang loss formula is derived using this argument, and then there's an exercise, which is Exercise 5, which asks you to extend that argument to the case in which the block customers wait in a queue. And so I may discuss that in class, because you have the exercise and you have a complete solution in the solutions manual. So I may do that quickly in class because it's information I want you to know, but I don't want to make a big deal of it now. So that's one direction. And then the other direction is to understand better what's going on, what's meant by a Poisson process and all that. Okay, so along that line, what I want to do is I also want to justify this stuff by simulation. So I want to give you an old homework problem, which I'm not going to ask you to hand in, but I want you to think about. Okay, but eventually I will ask you to hand some stuff in. And the simulation is to simulate the Erlang B system and to show, because it doesn't prove anything, it just will seem to agree, because simulations never prove anything, they're just examples. But I want to illustrate this theorem that the arriving customer and the outside observer see the same thing if I have Poisson input. I want to illustrate the insensitivity with respect to the service times, but sensitivity with respect to the inter-arrival times. So the simulation will show all that. So in order to do that, I got to do three things. First, I got to go through the logic of the simulation. Then I have to show you how to generate random variables that have any specified distribution in the simulation. And then I have to explain why the Poisson process and the exponential distribution and so forth are what they are. So some of this stuff is a review of elementary probability, things you're supposed to know from the prerequisite course. And some of this stuff is related to this course. Okay, so let me give you some information about what we're going to do so you can read up on this. Any questions about this before I erase it? Okay, first of all, the rate up equals rate down. That's an example of what's called a birth and death process. And this name comes from the idea biological modeling of a population, in which you've got a population and the population grows as members of the population give birth, and it decreases as members of the population die. And the analysis in that context actually carries over to queuing theory, because you can look at the births as being arrivals and the deaths as being departures, and so it's the same thing. So this stuff is in all the standard books on stochastic processes. So you go to any elementary book on stochastic processes, look up birth and death processes, and it's all there. In the textbook, this is covered on pages 14 through 26. So I'm going to cover birth and death processes, also something called statistical equilibrium. Again, I'm not sure how much of this I'm actually going to do in class and how much of it I'll just leave as reading. Partly that'll depend on you. If you ask questions, I'll do it, answer the questions in class. If you don't, I'll assume that that the reading is sufficient. As far as the way it's covered in the textbook, remember that this is a queuing theory book, so that the mathematical foundations are there for review. So maybe this is sort of a fiction or an excuse, okay? But if you're writing a book in which there's some kind of application and that depends on some prior mathematics, you can't really cover the mathematics totally, because otherwise you're writing a different book. But if you put in nothing, then it doesn't hang together and people get confused. So what you do is you put in you abstract something and you put in the core of what you think is important, but you don't treat it very rigorously. So then the person who already knows this stuff will read this and it'll be a review, and the person who doesn't know this stuff, well, then they know what the names of things are, and then they can go to their book on stochastic processes and look it up. But for our purposes, actually what I think is in this book is sufficient. You don't really have to understand the mathematics at a deep level. In any event, what I'm asking you to do is read pages 14 through 26 in the textbook, and then if you need to go further, look at the references. And this will try and explain where the rate up equals rate down equations come from in a more precise sense, rather than just saying, well, I'm going to equate these things using an argument that I've just shown you is totally false, because I tricked you at every stage by smushing around with the language. Okay, now it's also true that we have to worry about the particular distributions involved, and I'm going to discuss this in more detail in the class. Exponential distribution, the Poisson distribution, or Poisson process. And these things are discussed in the book on pages 42 through 62. But again, things are just picked out that relate to queuing theory. And so some of the things in here are, you might view as sort of obscure and also maybe not totally rigorous. So from my point of view, when I teach it from the book is good. But if you were reading it and trying to learn it on your own, this is probably not the first place to start. So just keep this in mind. Skim this stuff. As I say, we're going to go back over it in class. But let me give you other references for this. Okay, now, in the undergraduate course, the STA 4821, that's stochastic models for computer science, and that's the prerequisite for this course, at least in principle. Because in practice, we don't really cover this stuff in enough detail because just can't get that far. But that's the purpose of this course, is to provide the background for this course. All right, the textbook that we're using in that course is by Ghahremani, G-H-A-H-R-A-M-A-N-I. And I think it's a pretty good book. And it's in the library on reserve. You don't have to buy it. If you go to the library and ask for the reserve material for this course, STA 4821, this book and the solutions manual are there. Okay, now in this book, these are important topics. Density and distribution functions. Again, this stuff is supposed to be a review now, because remember, this is from the prerequisite undergraduate course. So density and distribution functions. And that's covered in that book in chapter 6. And then there are three important kinds of random variables. The Poisson random variable, Poisson process, is covered in section 5.2. The uniform random variable is covered in section 7.1, and the exponential is covered in section 7.3. Of course, any good textbook in elementary probability will have these topics in them. Okay, so what I want to do now is I want to go back to this model, this idea here, the Erlang loss system, and I want to go through the logic by which I'm going to simulate this. So first, let me pass this out. This is actually homework 1 from the 6260 course. Remember, you don't have to hand this in. This code is in BASIC. Of course, you can always translate it to something else. If you do that, you can make it run a lot faster, but you also probably you can introduce your own errors. I like to use BASIC because it's really simple. And it runs on my virtual computer, which is a Commodore VIC-20, which I bought at Toys R Us for $39 in the early 80s when PCs first came out. It was a real bargain. Of course, it broke. It's not worth fixing. So I don't have the computer anymore, but I don't really need it because I know it's going to happen anyhow. So I just say it's a virtual computer. So I run all these programs on my virtual computer. Okay, now, here's the strategy. So the purpose of this is partly to get this idea of simulation going, and also to illustrate, help you understand the meaning of these theorems that I just put down, none of which I proved, but which I will prove. Okay, so here's the system I want to simulate. Here's my timeline, and then here is server number 1 and server number 2. And so forth. In the simulation, you can have any number of servers. For the sake of this diagram, let me say that there's 3 servers. And what happens is you imagine that you have 2 urns. And one urn generates the inter-arrival times, and the other generates the service times. This is the notation I'm using. IA for inter-arrival, X for service time. I think that's what I used in the simulation. Yeah. And you imagine that the inter-arrival times, remember now that I said the arrival process is some random process that generates these arriving calls. So the way I'm going to generate the arriving call, the way I think of it is, I have this urn with tickets in it. And each ticket has a number. And the number corresponds to the inter-arrival time, which is the time between calls. So whenever I generate a call, I pull a number out of this urn at random. Of course, how I do that, that's the question of how I generate random variable values with a given distribution. But I pull this number out of here, and I put that value on this axis, and that advances my clock by that amount. And then I do some processing, whatever else I'm going to do, and then the next time I want to generate a call, I reach into this urn, I pull out a number, and I take that inter-arrival time, I add it to the old inter-arrival time, and that advances my clock by that amount. Now, there's 2 elements of randomness in these kinds of problems. One is the inter-arrival times, the other is the service times. So likewise, when I want to generate a service time, then I pull a ticket out of here. And the way I specify the different distributions of service times and inter-arrival times, well, I do that. I have to explain to you how I'm going to do that, how I'm going to generate the ticket values here to have any given distribution, namely to get a Poisson process, and the ticket values here to have any distribution, whatever I may want it to be. And then once I have the logic of the simulation, it works no matter what these things are. The only thing that changes is the particular numerical values. So here's the strategy behind the simulation. Here's time 0. The first thing I'm going to do is I'm going to reach into urn number 1, this urn. I'm going to pull out a ticket. I'm going to take its value and I'm going to measure it off here. So maybe it comes to here. So that means that this is the value on the ticket, this length. That's the inter-arrival time. Okay, so here's the IA. And this time here is the absolute arrival time, A. Then I look at trunk number 1. Now, before I start, I have in memory, I have an array which has these values, C sub j, C1, C2, and so forth. And each of these values tells me the time at which this trunk, number j, is next going to be available for service. So initially, the values here are all 0. All the trunks are available. The system is empty. So when the first arrival occurs, what he does is he looks at trunk number 1, and in the simulation, trunk number 1 will be available. So once it's determined that trunk number 1 is available, then you come down here and you know that the call is going to be carried. So what you want to know now is how long is that call going to last. So you pick a number from the urn that has the service times, and then you make trunk number 1 busy for that length of time. Okay, so the value, this value right here is x, whatever I drew out of that urn. And then I go back to this urn and I draw the inter-arrival time for the next call. So maybe that turns out to be here. So I take that value and I add it to this value. So this is going to give me my new A right here. See, running out of ink here. So what this call would do is it arrives at this time and it looks at trunk number 1. It finds trunk number 1 busy, so now it looks at trunk number 2. In our diagram, trunk number 2 is idle, so it makes trunk number 2 busy for a length of time determined by choosing a service time from this urn. Then it generates the next arrival. Maybe that occurs right here. At this instant, it looks at trunk number 1 and it sees that trunk number 1 is now idle, so therefore it makes trunk number 1 busy, and it makes it busy for a length of time equal to a value that it draws from this urn here. And then another call arrives. And this call finds trunk number 1 busy, trunk number 2 busy, trunk number 3 idle. So it makes trunk number 3 busy for its service time. And then maybe another call arrives. And this call finds trunk 1 busy, trunk 2 busy, trunk 3 busy. It overflows. And you just keep on generating these things and keeping records for each trunk as to whether it's busy or idle. And then you try and put the calls on the lowest numbered idle trunk. And when you finally get to trunk number S, if it's busy, you overflow. And then you calculate, after you've done this for enough calls, then what you do is you calculate the performance measures. In particular, I calculate the probability of blocking by counting the number of calls that overflow and dividing by the number of calls that's offered. That's the arriving customer's viewpoint. And then I calculate the outside observer's viewpoint by looking at all the times during which all the servers were simultaneously busy and adding those up. For example, in this case, this time right here, that's the time during which all 3 servers were simultaneously busy. So I would take the ratio of that length of time divided by this length of time, however long I had simulated, and that would give me the fraction of time that I'm in the blocking state. Now, by our theorem, which is called pasta, by the way, I didn't write this down, but I'll write it down now. The theorem says that if the arrivals occur according to a Poisson process, then the two measurements in principle will be the same. And although the converse isn't always false, or in this case it is, meaning that for the examples I'm going to give you, when the arrivals do not occur according to a Poisson process, then the two measurements will be different. I've selected examples so that they'll be greatly different so you can see the effect. POSTA stands for Poisson arrivals C time averages. This wasn't actually in the book because this theorem was finally proved in a way that everybody accepts it now as being mathematically rigorous, and this acronym was first applied in '82, and the book came out in '81. But nevertheless, it's in there because, and proofs are given because it was known, but not in a completely rigorous sense. Okay, so all we're doing now is we're going to simulate this thing and verify by simulation, by observation, that yeah, it looks like it's true. So let me go through the code for the simulation. You'll see how simple it is. That's the strategy. And then later I'm going to ask you to do things like this yourself, like write this kind of program to simulate systems that are similar to this. Okay, so here's the basic program. Again, you can write it in C or something like that in a smaller number of instructions, but to me this is the easiest way to do it. Okay, so statement number 100. Now if you don't know BASIC, by the way, BASIC is like the easiest language to learn. In fact, it was written for the purpose of teaching programming to non-programmers. So no computer scientist will ever admit that he uses BASIC. And so even though this is on tape, this is never to go beyond this room or anybody who's watching this tape that we professional computer scientists and graduate students are actually using this language, BASIC, written for idiots. But for our purposes, it's really the easiest and best way to do things. Now, the structure of BASIC is the same as Fortran. So if you know Fortran, you already know BASIC. And in any event, you can learn BASIC in an instant. And it's available on all the PCs, although there are different versions of it. So you got to make sure you can run into some kind of syntax problems. And because this is really a child's language, when you make a mistake, the computer doesn't always pick it up because there's no structure here. So it just lets you. The fact that it's very flexible is good because you can do basically what you want, but it's bad because if you make a mistake, it doesn't correct you. It just lets you hang there. Okay, so the first thing is I'm going to dimension. In this case, I'm choosing the dimension for 50, which means that in my program, the maximum number of trunks that this thing will handle is 50 trunks. So it allocates a list of 50 locations and each location here is going to measure the state of that trunk, because I want to be able to tell you in each case whether the trunk is busy or idle. Okay, so I'm going to dimension for 50 trunks. Next statement, 110, is an input statement. And I'm going to input S, which is the number of servers, and N, the number of customers to be simulated. So I think in the homework problem, what I asked you to do was 10 servers and 10,000 customers. There's another piece to the homework problem, which I haven't handed out yet, which is the specific input parameters. Okay, but this specifies how many servers and how long you're going to run the simulation. Of course, the length of time you run the simulation is chosen as a trade-off between how impatient you are and how long you have to run it to get statistical stability. Okay, the next statement, 120. The number of calls, number of customers simulated so far, is equal to whatever it was plus 1. And the way BASIC works is that everything defaults to 0. So if this variable, number of NC, has not previously been defined, then it'll be taken as 0. So the first time I execute this instruction, number of calls is 1. Statement number 130. Okay, now what I've done here when I execute this instruction is I've generated the first call. Actually, I don't need any inter-arrival time for the first call. I might as well call that 0. Okay, so I'm going to generate the first call. And now I'm going to look for the trunk that's going to hold it. And I'm going to index the trunks by j. So this is j equals 1, j equals 2, j equals 3, and so forth. So I start off j equals 0. Statement number 140. OK, now I'm going to generate the first inter-arrival time. I just said that I could have, when I generated the first call, I could call that time 0 if I wanted to. But according to this, I'm not. I'm going to generate an inter-arrival time so that I don't have any, so that everything is the same. I don't have any boundary in a sense here. OK, so I'm going to generate the inter-arrival time. So when I execute this instruction, I'm reaching into this urn and I'm pulling out its ticket. And the number on the ticket is going to tell me when this arrival occurs. But in the handout, I haven't said what this is. In fact, there are going to be 4 different cases. I'm going to generate exponential inter-arrival times. That's Poisson input. And constant inter-arrival times. And same thing for the service times. So there's going to be 4 combinations. So part of the homework problem was to write the instruction that generates the inter-arrival times with the distribution I want. And I have to show you how to do that. OK, but part of the point here is that this is just what drives this particular simulation. But the physical structure of the system is the same. It has nothing to do with this particular case. All this does is specify the particular input number that comes out that particular time. All right, statement number 150. 150 says that the arrival time is equal to the old arrival time plus the inter-arrival time. So I came over here, I pulled an element out of this, and I added it to the arrival time, so that moves the clock forward by an amount equal to the time between arrivals, the inter-arrival time. Statement number 160, j equals j plus 1. OK, so originally j was 0. Now j is 1. What this is saying is I am now going to look at trunk number 1. The call has arrived, and I want to find the trunk to put it on. So I'm going to look at trunk number 1. If it's available, I'll put it there. If it's not available, I'll look at trunk number 2, and then trunk number 3, and so on. OK. Now, statement number 170. If the value of j is equal to s plus 1, then I want to set k equal to k plus 1. OK, of course, initially, j is going to be 0. So the first time I go through this loop, j is going to be 1. But in general, j will have some value. And if when I add 1 to it, the value turns out to be s plus 1, that means I'm trying to put the call on the trunk beyond trunk s, which means it's an overflow call. So if that's true, then what I want to do is I want to count that as an overflow call. So I'll count that by k. So the first overflow call, this is a 0. And so the k would then be 1. OK, statement number 180. If j equals s plus 1, then I want to go to 290. All right, now 290 is a routine that takes care of some statistics for overflow calls. OK, now let's suppose I haven't gone to 290. If I haven't gone to 290, what that means is that the call that I just generated did not overflow. So that means that the trunk j, whatever j is now, that trunk was found idle. And so I'm going to carry the call on that trunk. So now I say, if my arrival time, or I'm going to carry the call on that trunk, I'm going to look at that trunk. OK, so we're looking at this trunk, and we ask whether the arrival time is less than c of j. And if it is, then I want to go to 160. Now, c of j, remember that we had dimensioned this array, this list of c, and c of j is the time at which trunk number j will next be available for service. So a is the current arrival time, and c of j is the time in the memory position that corresponds to the state of trunk number j. If my arrival time is less than this number, that means that this trunk is busy, and so I want to look at the next trunk. On the other hand, if the arrival time is not less than this number, then that means that this trunk became idle again before this arrival, and therefore the call can be carried on this trunk. So if my arrival time is less than the time in memory that says when this trunk is going to become available, that means if this trunk is busy, I'm going to go to 160. When I go to 160, I increment my trunk number by 1. I ask whether or not the call is overflowed, and if it hasn't, I ask whether my arrival time, which is the same as it was before, is now less than the number in the next slot of this list. In other words, whether trunk number, the next trunk in the order, is available for service. If the arrival time is less than that value, then that trunk is busy, and I go to 160, and I'm looking at the next trunk. So I'm going to continue through this loop until either the call overflows, in which case I drop out because I go to 290, or I don't drop out. That is, if this is not met, if this condition is not met, and instead of going back to 160, I'm going to take the next instruction in sequence, meaning that the next trunk is going to carry this call. Okay, so statement number 200. At this point, if we get to 200, what we know is that the time at which trunk number J is next available for service is prior to the arrival time, and therefore the call is going to be carried on trunk number J. So now I know the call is going to be carried, so that means I can select the service time to see how long that call is going to last. Okay, so statement number 200, x equals. Now, that statement is analogous to this statement. Here, I generated the inter-arrival time by conceptually pulling a number out of this urn. And now here, I'm going to generate the service time conceptually by reaching into this urn and pulling out a number. Okay, so I've got to write the instruction that generates the inter-arrival times and the instruction that generates the random service times. Okay, but let's say we've done that, and now x has a particular value. Okay, statement number 210. 210 says Sx is equal to Sx plus x. Okay, what I'm going to do here for use later is every time a call is carried, I'm going to accumulate that value in a counter called Sx, some of the x's, so that at the end I will know the total carried load, total amount of time of call minutes that the system carried. Okay, that's 210. 220. C of j is equal to a plus x. Okay, we know the call is being carried on trunk number j. So when is that trunk next time going to be available for service? Well, a is the current clock, and x is the length of the call. So this trunk is now going to be busy until time a plus x. So that's how I take into account how I make the trunk busy for the call that's being carried. Okay, that's 220. Now, 230. All right, so what I've done now is I have put the call up on trunk number J. Now, let's see, I don't think I'm going to go through, well, all right, let me go through it. Now what I want to do is I'm going to determine the value m, which is going to be the shortest server completion time. In other words, I've got all these, let's say I'm sitting over here someplace, and this guy has just been put on a trunk. So now he's been put on a trunk, so that means that the system is going to be busy, or that trunk is going to be busy for that service time, and these other trunks also have service times that end in the future, and this guy may or may not be busy here. And what I want to know is I want to know, measured from here, what is the shortest time until the trunk is going to be available. Because the time from here until the shortest time, let's say for the sake of argument it's this one, that means that during this interval, all trunks were simultaneously busy. And since I want to be able to count the fraction of time during which all trunks are simultaneously busy, what I want to do is I want to know how much time from the arrival time there is from the arrival time until the next time that there's an available trunk. Okay, so that's what this routine is going to do. It's going to set this minimum to be C1, then it's going to compare it with the others, and it's going to go through this list and pick out the smallest one. So that's fairly straightforward. Okay, statement number 240 says for I, some index running from 2 to S. Okay, so it's going to run from here on up to the top. And then as it goes up, it says if the element for trunk number I, the time at which trunk number I is going to become available, is less than M, then set M equal to C of I. That's the minimum so far. And 260 says, well, just go through this whole list, next I. So when I drop out, let's call this instruction 275. I made a little improvement over what was handed out to you. When I drop out, I have this value of, I know the value of the time. I know which trunk it is, and I know how much time it is until a trunk is next available. Okay, so now I say that if the M that I just computed is greater than A, that means, like in this diagram it is here, that means that there's a positive length of time during which all trunks are continually busy. So if M is greater than A, then I want to set AB, which stands for all trunks busy, equal to whatever it was before, plus M minus A. So in other words, the total time during which all trunks are simultaneously busy has been incremented by M minus A. And of course, if M is not greater than A, that means that I don't want to add any increment, so there's no change in whatever AB was. Okay, 290. If NC, the number of calls specified, a number of calls that's been run through the system, is less than N, which is the number of calls specified here, then I want to go to 120. Okay, 120 generates increments N by 1, and then goes through the whole process again. It sets J back to 0, generates new call, and so on. Okay, so this is just says, am I finished or not? If I'm not, go back to 120. If I am, then print my summary statistics, statement 300. So I want to print. Okay, now here's what I'm going to print. First, I'm going to print K divided by NC. Now, K counted over here. Let's see, where was K? K counts the number of overflows. Where's the instruction that does that? 170. Right. Okay, so this is the total number of calls overflowed. The denominator is the total number of calls generated. So that's going to give you the arriving customer's viewpoint. This is the fraction of calls that were actually blocked or lost in this system. Then I'm going to print AB divided by A. AB is the total time during which all trunks were simultaneously busy. A is the total time that was simulated. So this is the ratio of those times. It's the fraction of time that the system is in the blocking state. So according to PASTA, if we have Poisson input, then this fraction, which is the ratio of numbers, ratio of integers, and this fraction, which is the ratio of times, should be the same, closely. And conversely, if we have input that's not Poisson, these things will, in general, be different. And finally, it's going to compute Sx over A, which I'll get to later. This is the sum of the service times. This is the total time simulated. So this is actually the total work done per unit time. It's a measurement of what's called the carried load. Okay, and that's it. So what I want to do next time is show you how to generate and explain why. How you generate the Poisson input, and how you generate the service times with whatever distributions you want. We're actually going to use only, for this case, 2 cases. Exponential distribution here will make this Poisson input, and so I'm going to use exponential and constant and exponential and constant, so that's going to give us 4 combinations. And then you run this with those 4 cases, and you print out the values. You compare that with what the theory predicts, so that's from the formulas, which again I'll go through next time, and I'll show you the answers, and that's it. So, okay, so what I'm going to do, I actually need about 5 more minutes. Let me pass out the second sheet, and if you know how to do it, go ahead, and if you don't know how to do it, don't worry about it, because I'm going to discuss it in class next time. Because remember, what I'm doing now is I'm simply reviewing the stuff from the other course. Okay, any questions before we quit? Okay, no class on Monday, so see you on Wednesday.